Hi and welcome to C.2 Wave Model. Delightfully short topic and actually quite an enjoyable one. I think you'll find the questions on waves pretty easy. The only two places you might trip up are to do with the graphs, and there's two types of graphs I want you to be aware of: displacement-time and displacement-distance. I'm going to go into a great deal of detail in them in this tutorial. And the other place you might slip up is not knowing your definitions correctly. You can lose a lot of marks by not knowing waves definitions properly. So that's something I really want you to learn as you go through this tutorial. We kick off our waves topic by learning two of the most important things. The first thing is the difference between a longitudinal and a transverse wave. Some key, great, easy marks to be learned there. And the second thing, by remembering that waves transfer energy, but they don't transfer matter. What does that mean? Let's find out. Transverse waves. I guarantee your teacher did the slinky demonstration. If they didn't do the slinky demonstration, I'm terribly disappointed for you. No, I'm not. It's not that good a demonstration, but it does show you exactly how transverse waves and longitudinal waves propagate energy. A transverse wave is where you wiggle your hand up and down, and these coils represent the particles in a wave. And what you notice is, when you wiggle your hand up and down, a wave travels along the slinky. But the particles themselves, all they do is they oscillate up and down. They don't move along the slinky with the wave. They oscillate up and down, and the wave itself transfers energy. And that is the fundamental definition of a transverse wave. It's where particles oscillate. Now, this is a fancy word for vibrate or move up and down. I really do want you to use the word oscillate because it shows that you're taking care over the precision of your scientific language. So when you're asked to define a transverse wave or state what is a transverse wave, you would say particles oscillate at right angles to the direction of energy transfer. Now, you know I'm going to ask you to pop this in your revision notes at the end, don't you? So why don't you get your revision notes out now and go to the definitions section and write this definition in now. And then we don't have to do it at the end, right? Particles oscillate at right angles to the direction of energy transfer. And examples of transverse waves are water waves and electromagnetic waves. If you don't know what electromagnetic waves are yet, never fear, we will be talking about that very shortly. The second type of wave is a longitudinal wave. Now, previously when we were looking at transverse waves, to make that wave happen, the hand was oscillating up and down. To make a longitudinal wave happen, the hand has to oscillate back and forth. Can you see here? And what that does is a wave still transfers that way. It's just a different kind of wave. It's a longitudinal wave. And this wave, instead of being made up of peaks and troughs, this wave is made up of compressions where they're all very close together and rarefactions where they're very far apart. And this time, again, the particles themselves don't actually move along with the wave and carry the energy. They just oscillate back and forth like that around their equilibrium position. They don't carry the wave across. So we could say that our definition of a longitudinal wave is not particles oscillate at right angles. We simply say particles oscillate, and again that's a fancy word for move back and forth, parallel to the direction of energy transfer. And examples of longitudinal waves include sound waves or longitudinal waves, and earthquake pressure waves are also longitudinal waves. You'll notice that both types of waves, the particles within the wave
oscillate around their equilibrium point. With a transverse wave, they oscillated up and down like that. And with a longitudinal wave, they oscillated back and forth like that. But they didn't actually transfer the matter, or the particles didn't transfer from one bit to the next. All they did was they transferred the energy, and the particles themselves stayed where they are. Go to your revision notes. 2 definitions, please. One for transverse and one for longitudinal. And then head to the other notes section and write down waves transfer energy and information without transferring matter. We're going to go through a number of terms in this short tutorial that can be used to describe a wave. Look, I'm going to level with you here. You need to know the definitions of pretty much all these terms. So as we're going through the tutorial, how about you get your revision notes out and we go to the definitions section and you just write down the definitions as we go along. Here's a common type of diagram or graph that represents a wave. The wavelength, and we can see that here, my wiggly line, is the distance from one point on one wave, so this point here, to the equivalent point on the adjacent wave or the next wave. Now it doesn't have to be the 2 crests. It could be the 2 troughs. It could be the 2 sort of parts where it crosses the axis. It doesn't matter what point it is on the wave, as long as it's the equivalent point on the next wave. This definition has to be memorised, so let's pop that in your definition section. The next characteristic of a wave is talking about the amplitude, and the amplitude of a wave is the maximum displacement of a point on a wave away from its undisturbed position. Gosh, that sounds difficult. Well, the undisturbed position is here, otherwise known as the equilibrium. If the wave wasn't propagating and nothing was causing the wave to move, then all the particles would just be sitting on the equilibrium position. When the energy is put into the transverse wave, these particles start to oscillate around the equilibrium position. And the maximum displacement of the oscillation is called the amplitude. So the furthest away that particle gets as it oscillates around its equilibrium is called the amplitude. And of course, it oscillates on both sides, back and forth, like that. Again, this is another definition that has to be learned. Waves has a ridiculous amount of definitions to learn. Sorry, but actually it can be quite easy marks. And you can learn them quite easily using flashcards or Quizlet. So actually, it's good and it's bad. 3 more characteristics of a wave. The time period, or often just shortened to period, has a large T rather than a small t, because usually with time we have the small t, don't we? With time period, it's a large capital T. And it's defined as the time taken to complete one wave. So if you imagine, let's imagine something nice. Let's imagine you're sat on a lovely pier in a very hot, sunny country watching the sun go down, and a wave travels past you. If you were to measure the time taken for that whole wave to travel past you at that point, that would be the time period. It's the time taken to complete one wave. The frequency of a wave sometimes gets confused with the time period. The frequency is how many waves pass a point each second, and we'll go into that a little bit later when we look at their reciprocal relationship. But for the moment, can we just write down the definition of frequency as the frequency of a wave is the number of waves passing a point each second. And finally, the wave speed. The wave speed is the speed at which the energy is transferred through the medium. Now, when you see brackets in a definition or in an answer, it means it's nice to have, but it's not necessary. So if you wanted to write down the definition of wave speed, you'd say the speed at which the energy is transferred through the medium. And that can go in your definition section as well. Here we have in the top diagram here, we have a bird's eye view of, say, a ripple tank. And hopefully you've been shown a ripple tank in class. So we have the ripple tank from above here, and you can see the darker lines are the troughs of the wave. So the darker lines are these. And the lighter lines are the crests of the wave. And if you were to represent this real-life situation in the ripple tank in a diagram, what you would do is you draw a wavefront diagram. And it's basically lines showing the crests of a wave. A wavefront diagram basically illustrates the arrangement of the wave's crests as they travel. And the wavefront diagram can be quite useful when you are looking at refraction. Conversely, you may see something called a ray diagram. And a ray diagram illustrates the movement of the energy as the wave travels. So instead of drawing all the wavefronts, because let's be honest, that's a lot of work, we just draw one line with an arrow on the end that shows the direction of the energy travel. And again, this will become more clear when we look at reflection diagrams, refraction diagrams. But for the meantime, let's just be aware that you can represent waves using a wavefront diagram or a ray diagram. We come to the revision notes section, and we've talked about definitions, and I would like you to have the definitions of wavelength, amplitude, frequency, period, and speed here. And then in the common diagrams section, two diagrams. This diagram first, showing the amplitude and the wavelength. And this diagram here, you please draw it much neater than me, showing the wavefronts and the ray diagram.
Now you understand what amplitude, time period, wavelength, you understand what they all are. But one of the favourite ways that the IB assess it is using graphs. And what IB students don't usually realise is there's two types of graphs that you're constantly assessed on, but they look exactly the same. So let's go through those graphs now. Graph 1 is a displacement-time graph. So displacement in meters, time in seconds, and they tend to look like this. That maps the journey of one particle through a passage of time. On this graph, you can find out the amplitude. You can find out the time period. If you want to take the tangent of the graph at any time, then what you would find, tangent is at that point there, that's the instantaneous velocity. A longitudinal wave travels through a medium from left to right. Graph 1 shows the variation with time of the displacement x of the particle p in the medium. A1. State how graph 1 shows that the oscillations are not damped. Well, if they were damped, the amplitude would decay with time. The amplitude is constant, so our answer there is the amplitude is constant. If they were damped, we would expect the amplitude to decay. Question 2 says calculate the magnitude of its maximum acceleration. If you go to your data booklet, you would find that acceleration is equal to minus omega squared x. Now, given that acceleration and x displacement are directly proportional, then you would find that if when you're looking for maximum acceleration, you would use maximum displacement, and that's why I put A max equals X max. Omega squared is equal to 2 pi over T all squared. T is the time period, and we can see on here that the time period is 0.2 seconds. So
2 times pi divided by 0.2 all squared is do that again. 986.96. So 986.96 times 0.02, which is the maximum, gives us a value of 19.7 meters per second squared. I think we're going to have to approximate that to 20 meters per second squared, given that the rest of the data is given to a maximum of 2 significant figures. Question 3 says calculate the speed of the particle P at t equals 0.12. So at 0.12 seconds, this is, I'm going to click into the image now. So this here is 0.15 seconds. So 0.12 seconds is here. So we want to find the speed of particle P at that point there. Now we need to find the gradient of the graph at that point. So what we do is we create a tangent to the line. This is an acceptable way of doing it. There are other mathematical ways of doing it, but this is an acceptable way of doing the question. So we draw a line. That's not a very good line because I'm using a ruler on top of an iPad. You'd obviously use a pencil. You'd have a lovely pencil, you'd have a nice straight line with a ruler, and you'd create a tangent to the line at t equals 0.12. Once you've got your tangent, you then find out what the gradient of that tangent is. So v is equal to the change in x over the change in t, that's the gradient. So it's x2 minus x1 over t2 minus t1. This is x2, that's x1, this is t2, t1. So you pop your numbers in and you actually get a value of around about 0.3 meters per second. That is how you calculate the velocity from a displacement time graph. Oops, let's see if we can get rid of this now. So our answer there becomes 0.3 meters per second squared. Oh, not squared, meters per second. There are other mathematical ways of doing this. I actually find this is the easiest way and it's completely acceptable within the mark scheme. So this, let's not forget, is a displacement time graph. And what it allows us to do is calculate the time period of a particle or a wave at any stage, and that can be longitudinal or transverse. And it allows us to calculate the velocity. And the second type of graph that we found was the graph 2, and that was a displacement graph. So both x and y axes have displacement on them, and when we look at the wave, it looks exactly the same, but there's no time element to this. So between these peaks here, we're actually looking at the wavelength of the wave, and we still have the amplitude there as well. So this is, it's like you've taken a picture of a wave at a part of time. So there's no time element to this. It's an instantaneous picture. So on the y-axis, we've got displacement. And on the x-axis, we've got displacement. Centimeters and centimeters. So there, as I said before, there's no time element to this. It's like we've taken a snapshot of the wave. So we're not going to be able to find time period from here. What we can find is, we go into the picture, we can find wavelength. Whereas in the last graph, that exact measurement would have been time period. And we can also find amplitude. So
Let's go back. So we can find wavelength and amplitude. It says here, determine for the longitudinal wave using graph 1 and 2 the frequency. Well, using graph 1, we can find out what the time period is, and we know that the time period is, click in, the time period is this. 0.2 seconds. So F is equal to 1 over T. So 1 divided by 0.2 is 50 Hertz. Oh no, it's not 50. It's 5 Hertz. Apologies. And question 2 says find the speed. V equals F lambda. F is 5. Lambda is the wavelength, so we can calculate what the wavelength is. 420, so it's 16 centimetres. Is 0.8 meters per second. So again, let's go over this. This is a different type of graph. This is a displacement graph. And from a displacement graph, you can find wavelength and amplitude. So this is a repeat of the second graph, and we've now got a new diagram here. It says the diagram shows equilibrium positions of 6 particles in the medium. So there are 6 particles in this medium, and they sit at 0 centimetres, 4 centimetres, 8 centimetres, 12 centimetres, 16. They're all 4 centimetres apart. Okay. On the diagram above, draw crosses to indicate the positions of these 6 particles as the instant of time when the displacement is given by graph 2. So the 0 particle, 0, has 0 displacement, so that stays where it is. The 4 particle at 4 centimetres when it's at equilibrium, so let's go here, has now been moved 2 centimetres to the right. So it's going to be 2 centimetres to the right, 1, 2. The 8 particle here is still in equilibrium, so that doesn't change. The 12 particle has now been moved 2 centimetres to the left, so 1, 2, it's there. Number 16 particle stays where it is, and the 20 particle has been moved 2 centimetres to the left, to the right, sorry, up here, so 2 centimetres to the right, let me think, 1, 2, and it goes there. So we now have the displacement of each of these, well, the position of each of these particles shown on this diagram here. On the diagram above, label with the letter C. A particle is at the centre of a compression. A compression is where the particles bunch together. So this point here is where the particles are bunched together. That is our compression. And the particle is at the centre of the compression, is the one in the middle, C.
How much do physicists love equations? Loads! That's why we've got some equations for waves as well. And actually, we're so clever and we're so inventive, we've called one of them the wave equation. And that links speed, frequency and wavelength. We have another equation that is often misinterpreted and not used very correctly by students. And that is a reciprocal relationship that explains time period and frequency. We'll go through that right now. Well, let's go through the wave equation first. The wave equation is something you're probably very familiar with. It's a very common equation in physics, and it basically is V equals F lambda. V stands for the wave's speed, and we have a definition for that in our notes already. Speed is measured in meters per second. Frequency, again, we have a definition for that already, is measured in hertz, and hertz is a measure of how often something happens per second. Finally, lambda, it's a Greek letter, represents the quantity of wavelength, and wavelength, because it's a length, it has units of meters. If you were to use an equation triangle, then you'd have V here, F there, and lambda there. Now, if you are ever asked to write down the wave equation as part of an exam, please never write this equation triangle as your answer. Examiners don't like it and you get no marks. Just write this down. Here's the frequency time period relationship that many students either forget or don't use correctly. So let's have a little chat about it now. I'm going to do something kind of weird and I'll see if it works. I'm going to tap this microphone once every second. Ready? Why did I do that? Well, what I was doing was I was tapping with a frequency of 1. And the time period of those taps, so the time it took for one tap onto the next tap, was 1 as well, 1 second, and 1 hertz. What I'm going to do now is I'm going to double the taps. So I'm going to do 2 taps per second. The frequency of that, there were 2 taps per second, so that's 2 hertz. And the time period was half a second, because the time between each tap was half a second. Let's do it 3 times. The frequency is 3 hertz. The time period is 0.33 hertz. Let's put time period into other way. Rather than writing in decimals, let's write it in fractions. Can you see that as your frequency goes up, your time period goes down by 1 over the frequency? So that's what this relationship is. This relationship is saying if your frequency goes up to 10 hertz, something happens 10 times a second, it means there's a tenth of that as the time taken for that event to happen. I can't tap 10 times a second, or can I? Let me try. Ooh, I've lost control. That is the relationship here. F equals 1 over t. And of course, if you multiply F times t, guess what you get? Number 1. Job done. Let's go to your revision notes in the formulae section. You need to memorise this equation. So let's write down a little star beside that. And you need to be able to use this equation. This section of waves is where you can get some easy marks, really, but there is a bit of content you need to learn. And basically, the first thing I want to run through is describing the properties of electromagnetic waves. So we're going to look at the electromagnetic spectrum and identify the properties that all waves in the electromagnetic spectrum have. Then we're going to look at the electromagnetic spectrum, each section of it, and recognise, first of all, that it's arranged by frequency and wavelength, and memorise the uses of each type of radiation. And finally, I just want to really point out that the human eye can only detect a limited range of electromagnetic waves. Before we start, there is a song on YouTube that I do recommend you watch, and it's super annoying. Just search the electromagnetic spectrum song in YouTube. And if you're lucky, you might get a small rendition of it as we go through this tutorial. First of all, the electromagnetic spectrum. What is it? Well, electromagnetic waves form a continuous spectrum. That means that one region continuously joins on to the next region. And those waves or regions are grouped in terms of their frequency and wavelength. So if we start with radio waves, they have a very large wavelength, as shown here in the diagram. And it goes all the way up to gamma waves, which have a very small wavelength. And conversely, if we start at gamma rays, it has a very large frequency, so there's lots of these waves per second. And we go all the way down to radio waves, it has a very small frequency. So if the wavelength's big, the frequency is small, and if the wavelength's small, the frequency is big. They're the opposite. You can see there's 7 sections to the electromagnetic spectrum: radio waves, microwaves, infrared, Radiation, visible light, ultraviolet, X-rays, gamma rays. Okay, there is a small intro to the electromagnetic spectrum song. I'll try not to sing it again, but I can't promise anything. There's 4 things that these waves have in common. They're all transverse waves. So they all have the particles oscillate. Remember we talked about the definition of a transverse wave? At right angles to energy transfer. That is what a transverse wave is, and that is what an electromagnetic wave is. All of these waves travel at 300 million meters per second in a vacuum. I don't like writing 300 million. Too many zeros. So instead I write it in standard form. That's 3 times 10 to the 8 meters per second. They all travel at the same speed in a vacuum. As we saw earlier when we were looking at refraction, when they go into a more optically dense medium like glass, they'll slow down. But in a vacuum where there's no air, they all travel at the same speed. They can all travel through a vacuum. How do we know that? Well, heat, which is infrared radiation, and light get to us from the sun, don't they? And the sun is in space, and space is a vacuum. So these waves must be able to travel through a vacuum because they reach us here. It's light and it's hot. Well, sometimes. I live in Scotland, it's never hot. Finally, number 4, all electromagnetic waves transfer energy from the source of the waves to an absorber. I'm absorbing light, I'm absorbing heat. I can absorb X-rays if I've got broken bones. They all have the possibility of transferring energy from the source of the waves to an absorber. These 4 properties of electromagnetic waves, they are the same for all of the types of electromagnetic waves, and I would like you to write them down in your other notes section. Let's go through each in detail. Well, I say detail, we'll talk about what they're used for and if there's any dangers. Radio waves have the largest wavelengths, as we talked about a second ago. They are used for television and radio. That's their uses. And there are no known dangers of radio waves because they've got very low energy. So we don't have to worry too much about them. So all we need to know about radio waves is they're used for television and radio. Microwaves we're spicing things up a bit here, used for more things. They're used for radar, which is a radar here. Get them in a control tower for an airplane. Mobile phones, we can't live without them, can we? Satellite communications and cooking. You should know these 4 uses of microwaves. There's a small danger of microwaves in that our body tissue contains water molecules, and water molecules can absorb microwaves and become hot. So if you shoved your hand in a microwave, there is a danger there that you would get very hot. So please don't shove your hand or any other part of your body into a microwave. Infrared radiation, otherwise known to us as heat, is used for electrical heaters, cooking food, and infrared cameras. If you were to put your hand underneath a grill and experience infrared radiation, you would have a danger of skin burn. So what do you need to memorise about infrared radiation? Its uses: electrical heaters, cooking food, and infrared cameras. Visible light is used for, uses are, fibre optic communications and for humans to be able to see, because our eyes only detect visible light. So we only detect a tiny limited range of the electromagnetic spectrum. It's a narrow band of wavelength and frequency. Now, very bright light can damage the sight, and that's why we ask you never to look directly at the sun, because it is a very bright light. Ultraviolet radiation is used for security marking of money, energy efficient lamps, and sun tanning. Please don't suntan. It's not good for you at all. Because, despite the uses being sun tanning, I would rather you didn't use that in an exam, but you can if you like. It can cause the skin to age prematurely, so you look older than you actually are. and it increases your risk of skin cancer. Nobody wants that. X-rays. X-rays are used for medical imaging and treatments. More for medical imaging, I would say. X-rays are ionizing. That means it can mutate the cells and cause cancer. So there's your danger. They get more dangerous as they go up the electromagnetic spectrum because they've got more energy. An X-ray has much more energy than a radio wave. And the use is, I would say, medical imaging rather than treatments. Finally, we have gamma rays. They are used for both medical imaging and treatments. So the uses are two things. They originate from changes in the nucleus of the atom. That's interesting. Let's talk about that later. And gamma rays are ionizing. Just like X-rays, it means that they can cause the cells to mutate and can cause cancer. But they can also cure cancer. What a fickle thing X-rays are. Go to your other notes section, please, and let's write down the 4 properties of electromagnetic waves. They're all transverse. Make sure you know what we're writing about here. EM waves. All transverse. They travel at 3 times 10 to the 8 meters per second. Can be absorbed. A material interface. And can travel through a vacuum. Then you can either go to the common diagram section or you can just do it here and draw something that's going to help you show the electromagnetic spectrum. That's terrible. Radio waves, microwaves, infrared, radiation, visible light, ultraviolet, X-rays, gamma rays. The electromagnetic spectrum, it's just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared, radiation, visible light, ultraviolet, X-rays, gamma rays. Can you see that I've put the electromagnetic spectrum in order and I'm putting the uses of those different regions of electromagnetic spectrum in my notes? Can you do the same, please? Thanks. Let's have a think about sound waves. Let's think about how they're generated and how we hear them. Good, 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 good vibrations. Good, 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 good vibrations. Did you see my increase in frequency there? Hope you like my singing, but let's talk about good vibrations and how they produce sound. All sounds are produced by vibrations, and what I've got here is the cross section of a loudspeaker. This here is a membrane. This here actually is a magnet inside it, and what this membrane does is it oscillates back and forward. And by oscillating this loudspeaker membrane back and forward, what it does is it causes the air molecules around it to oscillate back and forth too. And what that causes is a cause of waves to take place where there are areas of high density molecules and areas of low density molecules that travel along the air. So as soon as the membrane starts to vibrate, it causes these air molecules to vibrate, which causes the air molecules to form waves, longitudinal waves, with energy transferring in the direction shown. And that means that sound is transferring in the direction shown. All molecules, every single one of them is vibrating back and forth, and it causes sections of high density called compressions and sections of low density called rarefactions. And these compressions and rarefactions, what they do is they reach your ear and they cause the eardrum to vibrate at a certain frequency too. And that vibration of your eardrum causes your brain to reproduce that as sound in your mind. So vibrating eardrum causes sound to be recognised. So what does that tell us about sound waves? Well, it tells us that sound waves are longitudinal. It tells us that sound can travel through solids, liquids and gases as long as there are particles that can vibrate, then sound can travel through it. But do you know what sound can't travel through? It's a vacuum. And why can't it travel through in a vacuum? Well, there's no particles in a vacuum, so the particles can't carry the sound. It can't carry the energy across. So that old saying, in space, no one can hear you scream. It's true. If you scream in space, it's going to be empty. It's going to be silent because there's no particles to carry that scream for you. That's what all the best horror movies are made of, that concept. So examples of what I've just suggested to you. We have a vibrating membrane, so this is a loudspeaker. So that vibrates, it's a solid, vibrates, and it causes longitudinal sound waves in the air to come to our ear. In a guitar, we have a solid that vibrates. What's the solid that vibrates in the guitar? It's the guitar strings. Okay? And by using this very clever idea of the bass of the guitar, or the body of the guitar, to echo and resonate the sound, we're able to hear a sound from a guitar. When we use a drum, what is the solid that vibrates? Well, the solid that vibrates is the skin of the drum. And that skin of the drum, again, is resonated, it's resonated, and the volume of the sound is increased to allow us to hear it. And finally, we have a solid that vibrates in a violin as well, and that causes sound. So there's a theme. The theme is that a solid vibrates at a certain frequency, and the air molecules allow a sound wave to travel towards us in compressions and rarefactions to our ears, where our eardrum vibrates in unison. Now, if that vibration is done at less than 20 hertz, and by 20 hertz that means, let's take the loudspeaker for example, because we've got some loudspeakers here. If the loudspeaker membrane vibrates 20 times per second, that means it's got a frequency of 20 hertz. This produces a very low sound that is almost inaudible to the human ear. So, I don't know if I can go as low as this, but like really low, the lowest sound ever that you can hear is 20 hertz. So if something vibrates at 20 times per second, any of these solids vibrates at 20 times per second or 20 hertz, it will produce the lowest sound you can hear. Any frequency below 20 hertz, so 0 to 20, is known as infrasound. And as the frequency increases above 20 hertz, humans can start to hear the sound. So let's say it goes like all the way up to top. All those sounds are a range of frequencies from 20 hertz all the way up to 20,000 hertz. So when something vibrates at 20,000 times per second, humans can, to a point, still hear that. And I say to a point because young people can hear that, but as you get older, your ability to hear sounds of that high decreases. And that sound is super squeaky and super high. And above that, the human eardrum can't vibrate physically any faster than 20,000 hertz. So anything above that is still a sound. It's just not a sound that we can hear. And it's known as ultrasound. But guess who can hear it? Dolphins. Dogs. Lots of different other species can hear ultrasound. It's just that the human ear is not built to hear ultrasound. Let's go to our revision notes. I'd like you to summarise this idea of a vibrating solid causing a sound wave and give some examples like a guitar, violin, drum, so on. And then just write normal human hearing. There's always an exception. There might be some crazy folks out there who can hear 22 kilohertz or something, I don't know. Is less than 20,000 hertz and is greater than 20 hertz. 20 to 20. I think that should be easy enough for you to remember. If I sang a note to you, like la, I know it was beautiful, right? And asked you to tell me what frequency that note was, you would not have a clue. There must be people out there who have that skill to take a note and know exactly what frequency it is. But I mean, let's be honest, we need a measuring instrument to find out what the frequency of a sound is. And you guys in your school do have a measuring instrument that can do that, and it's called an oscilloscope. Let's have a look at that in more detail. When you connect an oscilloscope to a microphone, then what happens is the microphone converts the sound waves into an electrical signal, and the oscilloscope takes those electrical signals and turns them into waves so we can see them. And this is what happens here. So you can see a sound wave by connecting a microphone to an oscilloscope. Can I recommend that you learn how to spell oscilloscope properly? It's the kind of thing that bothers physics teachers, examiners, and so on. So this is what the oscilloscope looks like, and you can see these waveforms of the sound on that oscilloscope. And a challenge that you need to be able to understand is to how to find the frequency of a wave from one of these oscilloscopes. Now you can see this trace of the wave on the oscilloscope, and there is something called the time base of this oscilloscope. And the time base is shown here. You can see that there's a knob that says time base, and it's got a range of scales, and it's directed to, the dial is directed to 1 millisecond. And 1 millisecond is equal to 1 times 10 to the minus 3 seconds, or 0.001 seconds. So each square horizontally is equal to 1 millisecond. And the distance between one point on one wave and the same point in the next wave gives us the time period of that wave. We can see the time period of the wave shown here is 4 squares, 1, 2, 3, 4. So the time period is equal to 4 squares, which is equal to 4 times 1 millisecond, which is 4 milliseconds, which is 0.004 seconds. And we previously learnt a formula saying that frequency equals 1 over t. So we put 1 divided by 0.004 and we come out with a frequency of 250 hertz. So this is how we find the frequency of a sound wave. We use an oscilloscope, a microphone, we look at the trace, we find out what the time period is, and we use our formula to determine what the frequency is. Let's have a look at a sample question just to formalise and embed this method into our heads. The time base in an oscilloscope is set to 0.2 seconds. So that means that each horizontal square is 0.2 seconds. Calculate the frequency of the sound wave shown on the oscilloscope. Okay, how many horizontal squares are there to complete the whole wave? 1, 2, 3, 4, 5, 6, 7, 8. So the time period of the wave is equal to 8 times 0.2, which is 1.6 seconds. So the frequency of the wave is 1 divided by time period. So that's 1 divided by 1.6, which gives us a value of 0.625 hertz. We want to give that to less decimal places, so let's go 0.6 hertz. That's not very much, is it? Can we hear that? No, it's under 20 hertz. So it will be infrasound. We can't hear that. Previously seen that we can have a sound wave represented on an oscilloscope. So we can see the trace of how a sound wave is represented by using a microphone, attaching it to an oscilloscope, and we can see a wave pattern. It'd be quite nice now if we could see and understand how the frequency of a sound or the loudness of a sound affects what the wave pattern looks like. Let's look at amplitude first. Consider we have a guitar string. I'm not going to draw the whole guitar, okay? But if we pluck that guitar string, it starts to vibrate back and forth, vibrates up and down. And what it does is it produces a sound. And let's say that frequency is 250 hertz, a really low sound like la. When you pluck the string of the guitar, the string vibrates and it produces a lower sound like la. And what that would do is you could attach it to an oscilloscope, your microphone to an oscilloscope, and you could see that the trace of that sound would look a little bit like this. Now, if we took the same string and plucked it harder so it had a bigger vibration, the sound would be the same. It would still be the same note. It would be la. It would be much louder. It would be la. And it would look like this. When we increase the loudness of a sound, the frequency doesn't change, but what does change is the amplitude. So you can see on this diagram here, let's label that 1 and 2. And number 1, the wavelength of sound wave is around about 1 and a bit boxes. And the wavelength of sound on this one is around about 1 and a bit. It's exactly the same wavelength, which means it's exactly the same frequency. But all that's changed is the loudness or the amplitude. The amplitude in situation 1 is a lot less than the amplitude in situation 2. So the lesson here is when the loudness, should we put volume? When the volume of sound changes, the amplitude changes. The wavelength and frequency of the sound wave trace stays the same. So you really have to start judging, if it gets louder, you have to show exactly the same trace, but a taller wave. And if it gets quieter, you show exactly the same trace, but a smaller wave. Let's have a look now to see how frequency, or the pitch of a sound, affects the trace of the sound wave on an oscilloscope. And we have 2 traces here. We have trace 1, which is the black one, and we have trace 2, which is the blue one. Can you see that the number of boxes that trace 1 holds for the wavelength or the time period of this wave is got 3 boxes? And the number of boxes for the blue wave is 2 boxes. And this is, if you remember, the x-axis is the time base. So that tells us that wave 1 has a longer time period than wave 2 because it's got a shorter time period. And given that f equals 1 over t, that means that wave 1 has a lower frequency, and relatively to that, wave 2 has a higher frequency. So wave 1 might sound like this, la. Wave 2 might sound like this, la. You'll notice that I did exactly the same volume, okay? So they have the same volume, and we know they've got the same volume because they've got the same amplitude. You can see both waves have the same amplitude. So despite them sounding slightly different pitch, they have the same volume. And you could go the other way. You could create a third wave that has a longer time base or a longer time period, which means it's got an even lower frequency. In fact, we can do that just now. You can see that our third wave has a time base that covers 6 boxes, which means that it's got a much lower frequency and a longer time period than situation 1. In fact, it's got double the time period in situation 1. And that means that it has half the frequency of the first wave. Now, maybe that's a little bit complicated, but what we can get out of here is it's got the same volume, it's just that the pitch has completely changed. And that's how we represent the change in pitch, and that's how we represent the change in pitch with the sound trace on an oscilloscope. Now, what would that mean if you actually had to... So we go to our revision notes and we go to common diagrams, and I would like you to draw something like this. And let's do loudness. We'll do one wave like that. And then a same pitch wave, louder. So you can see the wavelength is exactly the same. It's just got a higher amplitude. Amplitude is greater and it's louder. And let's do something similar for pitch. So we can see that the blue wave has a higher pitch, which means the frequency is greater, but it's got the same volume because it's got the same amplitude. So that little diagram there, I think, is probably quite useful to show what the trace of a sound wave looks like on an oscilloscope.